right, welcome back. This is CS50, and this is the start of week 1. So just a couple of announcements. One, so problem set 0 is due tomorrow by noon. Realize that there are 2 aspects to submitting. One is to actually upload to the Scratch website on MIT's domain, but also to submit the form and follow the instructions at that URL. That URL is in the PDF itself. Just don't overlook it. It's at the very end of the piece set that says how to submit. If you've not yet taken advantage of such, or did this week and want to in the future as well, do realize that for every one of the problem sets, there will be code walkthroughs led by one of our teaching fellows, Tommy McWilliam. And these are meant to be opportunities, again, to get you started on the piece set, specifically the standard edition thereof. Though if you do have questions on the Hacker Edition, Tommy is certainly happy to field those. These walkthroughs take place in Maxwell Dworkin, which is up the street at 33 Oxford Street. It always takes time to get everyone's ID card activated. So if you ever find yourself locked out of the building, just call 617-BUG-CS50, hit the secret option 0, and that will ring multiple folks on the teaching staff to help you solve that problem. Help.cs50.net. So do take advantage of this resource throughout the term. It's an opportunity to post questions, receive answers, and also see whether your classmates have asked similar questions as well. Office Hours 2 debuted 2 nights ago, and tonight and tomorrow they'll be taking place in Lowell House. Upon arrival, simply pull out your laptop and go to q.cs50.net, and if and when you have a question that you'd like to ask of the TFs and CAs, simply follow the simple 3-step process. What are you working on? What's your question? And click raise your hand. The CS50 greeter's iPad will then list your name in the order in which you've raised your hand, and he or she will then touch your name and that of a staff member as soon as someone's available, and your browser will start beeping and flashing at you saying it's your turn for help. So that is q.cs50.net. Realize, too, that we do hold office hours not only tonight, but again tomorrow night, so that if you do decide to cash in one of your 4 late days per the syllabus, you still have a support structure in place to take advantage of tomorrow evening as well. So refer to the syllabus for the details on how to cash in such things. Lastly, resources available in general. So realize that retroactively after a lecture, we will post a canonical set of scribe notes written by one of our teaching fellows, Andrew Sellergren, who's been with the course for some time and is very good at documenting what happens in class, as well as making snarky remarks in the footnotes. So hopefully you will enjoy reading the PDFs that will always be posted a few days after lecture on the course's website, particularly around quiz time, where they're a useful useful guide to what actually happened in class. What you'll also see appearing soon alongside the videos of lectures online is verbatim transcripts of every word that's uttered on stage here, so that you can search for keywords, topics of interest. If you didn't quite catch something, you can read as well as listen to and watch it online. And lastly, with regard to lectures, in the interest of preserving trees, we tend not to print many handouts, except for last week during shopping period, but realize PDFs of the slides, PDFs of source code, programming code that we'll start writing this week will always be available online if you want to print it yourselves or bring it on a laptop to tinker with it during class. Any questions of any sort? Anything at all? All right, so you've probably, if you're an upper class, oh, and sectioning, one last FYI. Sectioning will commence this weekend, but more on that this coming Friday at class. So indeed, we have one final Friday lecture this week. Thereafter, we are back on our Monday, Wednesday schedule. So odds are, if you're an upperclassman, you've walked past this thing for like 3 years in the Science Center and never once really stopped to think about what it actually is. Maybe you indulged during pre-frosh and actually read the little tourist-friendly signs describing what this thing is. But this is the first electromechanic computers named the Mark I from many years ago that was actually invented by a professor and a graduate student by the name of Howard Aiken here in physics, and it was meant to be an automatic calculator. I thought I'd rattle off a few fun facts here. Namely, 1, it did indeed handle some non-trivial amounts of math, namely up to 23 significant digits. So that in and of itself is impressive, and that could take a human some amount of time. But in terms of the weight, this thing was 10,000 pounds, and what you see in the Science Center is only a portion of it. Most of it has actually been dismantled. And in terms of its performance, a multiplication took 6 seconds, a division took 15.3 seconds, and a logarithm or trigonometric function took over 1 minute. So of course, contrast this with your Dell laptops, your MacBook Airs and whatnot, which maybe are annoying when they're 5 pounds these days to carry around in your backpack, and surely mathematically they can perform these calculations instantly. But I thought I would give you a sense of just how exciting technology was some years ago, replete with not only black and white footage and that voice that seems to be omnipresent from the 30s and 40s. This is a little look back. It's about a minute long as to the history and the utility of that Mark I computer you've been ignoring for some years here. User error.
A triumph of mathematical and mechanical skill is this great new automatic calculator at Harvard University. Intricate problems in mathematics, put through the machine in coded form on tape, are accurately solved in a minute fraction of the time required for human calculation. Designed to expedite all forms of mathematical and scientific research, the giant mechanical brain will work for the United States Navy until war's end.
It was a magical time. So do, if nothing else, thank you. Do, if nothing else, perhaps take a modicum more interest when walking past that machine, because there actually is a lot of compelling history there. And you might have heard terms like punch cards and tape with regard to how you actually feed input into a computer. Back in the day, you actually toggled switches, and you literally fed in cards, pieces of paper with holes in them that represented zeros and ones and other such instructions. We've moved beyond that, certainly now with our keyboards and such, but there's a lot of history on this campus in particular. So perhaps at least pause the next time you walk past. Last week, we introduced not only the course, and not only Scratch, but some of these fundamentals that we're going to now start to take for granted, namely how to represent information. And it's not that we're going to dwell on things like zeros and ones and bits and such in this course. We're very quickly going to start taking them for granted, that somehow we have this ability to store numbers and data. But just to tie this week to last week, I thought I'd see if we could get 8 brave volunteers to join me up here to hammer home one of last week's lessons. So how about you 3 there in the center? 4, 5, 6. Let's go over here. 7. And Rob. 8. Come on up. So you have to be comfortable, as always, appearing here on camera. We have 8 pieces of paper, 1 for each of you here. And if you could each align yourselves on stage, consistent with the order here. Rob, you will be, let's say, Rob will be number 1. Over there on the right, if you want to be the 2's place. If you'd like to be the 8's place, I'll find the 4's place in a moment. If you'd like to be the 4's place. How about let's see, come on, 16th place. And 3 more, 32's place, 64's place, and 128th place. So if you want to go ahead and up in front of the stage here so all can see, indeed hold your number outwardly. What these guys each have, and Rob, do you mind shifting down just a little bit? So we have now places 1 through 128. And recall one of the takeaways last week is that this system of binary, of base 2, is not all that dissimilar to what we've been using for years, namely base 10 or decimal, where we have the 1's place, the 10's place, the 100's place, and so forth. Instead, in the world of computers, we tend to use powers of 2, the 2 really deriving from the binary nature of bits, zeros and ones. And so our column placeholders are the 1's place, the 2's place, the 4's, 8, 16. In other words, instead of multiplying by 10, you multiply by 2. But we built up from this numeric capability last week to actually express numbers. And does anyone recall what the code or the system was that maps numbers to letters in computers typically? So it's something called ASCII, A-S-C-I-I, which is just a code, a mapping between numbers and letters. And recall that that mapping looked a little something like this. And the chart itself is certainly not worth memorizing, but a few key values like 65 for capital letter A, 97 for lowercase a, a few of those tend to be useful just to kind of ingrain in your mind so that they can be handy when we're actually writing code. Now, these guys have on the backs of each of their sheets here a little cheat sheet. It's round 1, round 2, round 3. And in each of these rounds, their little cheat sheet advises them to either raise their hand or just stand there. If they've raised their hand, they're meant to be representing a 1. If they're just standing there, they're meant to be representing a 0. We've got a 3-letter word to represent with an 8-bit byte, an ASCII character, if you will. So let's see what 3-letter word we can spell with these folks here. So if you all, as our volunteers, round 1, could raise or not raise your hand as instructed by your cheat sheet. What number first is being represented by these 8 volunteers? Yeah, 66, right? Because we've got the 64's place plus the 2's place. Add them together, get 66. And that letter then maps to? Capital B. All right, so we're on our way. How about round 2? What are we representing now? That's definitely not universal agreement. How about again? OK, I heard more 79. So if you just stole the person next to you's number, you are correct. So the number 79 maps to what letter here? B-O. OK, so now the third and final round. Round 3, go. What number do we have here? Yeah, so we have 87. And again, you can get this by adding up the numbers in front of anyone with their hand raised. 87 maps to a W, so W, and so we have a nice word here, bow, often pronounced by last year's class as bow, which didn't really make for a good ending. But if you would take your bow, we've indeed spelled out B-O-W. So congrats to these guys here. If you want to head off stage left, we have a little parting gift for you in the way of a waiver form. So we now have this ability to express numbers, to express letters, and so now let's start taking this for granted. And indeed, let's transition from last week's exploration of Scratch, which was very user-friendly and graphical, but also very limited. Even if you've never programmed before, you probably found it, or are finding it, or will find it, difficult to do certain things, because the program isn't necessarily as expressive as you might like it to be, or you're just not very familiar with it yet, so it just takes some time finding your way around. And allow me to emphasize at this point in the course, right before study cards are due, there's quite the spectrum of students in this course. And in the weeks 0 through 2, we typically run this risk historically of either kind of boring those more comfortable because they're coming in with more background. The goal of lectures in particular is to start filling in any holes that you might have from your prior experience, whether formal in classes or just self-taught. And for those less comfortable, making sure that we equip you with the same basic mental model and understanding of some basics so that all of us in just a week's or 2 time can start having a conversation on exactly the same level. Now, if you're finding that even Scratch is kind of stressing you out, is taking a ridiculous amount of time, realize that all of these things get easier. And consistently, every year, even when I took it myself, the best strategy in general, and maybe it's too late for this first piece set, is just start these things early. They'll typically go out the door. They'll go out the door by Fridays each week, which means you have the weekend if you'd like to sort of ease into it. The walkthroughs are on Sundays. And really, the key to programming is not to start on, say, Wednesday night and say, I'm going to finish this by morning or by midnight, because it's just not fun. And you can't think necessarily clearly, and there's just a huge advantage to being able to walk away from some problem. I've lost count over the years of just how many bugs I've solved just by randomly thinking about them passively throughout the day, and I'm like, oh, so that was what I was doing wrong. And to allow yourself that opportunity honestly makes things easier, makes things more fun, and certainly eliminates the stress that's inevitably induced in any course by postponing things to the last minute. So let me get off that soapbox there and now start to transition us to this programming language C. So today we begin a more traditional programming language. It's an older language, but it's the one that really sets the direction of a lot of today's modern languages, which we'll then begin to visit toward the end of the semester in the form of PHP and JavaScript and some other things as well. And what's nice about C, as we'll soon see, is that it's relatively simple. And it's not going to feel that way, particularly to those less comfortable, most likely the first week or so. But relatively speaking, you can learn this language in just a few weeks. Contrast that with some human language, a spoken language. You typically don't master a new language after just a few weeks of practice. It can take months, it can take semesters, it can take years. So just realize that the scope of the languages we're about to learn is actually fairly narrow. So here's a little program that we saw last week. When green flag clicked, say, "Oh, hi, world," something to that effect. So this was a script. The purple piece there was a statement, and statements, again, just do something. Well, just to kind of tease you with how we're going to start translating what's very user-friendly and very sort of graphical and playful into something that's a little more easy for a machine to understand. Starting today and beyond, if you want to write a program that just says something silly like, "Oh, hi, world," you're actually going to type in a text editor, like Notepad or TextEdit, whatever, or more fancy programs that we'll introduce, something like this: int, main, void, some curly braces, printf, and we mentioned printf last time, and "Oh, hi, world." So there's some crazy syntax in here, semicolons, curly braces, things that take a little getting used to, but you start to see these things recurring. So when you start to see code like this today and beyond, just realize, it's really just Scratch. It's really just those two puzzle pieces we saw last week, but the syntax now is a little more cryptic. It's not nearly as user-friendly, but you get good at it, I dare say, quickly. So statements in general. This was a statement, "Oh, hi, world." This would translate more directly just to this one line of code. So when we say things like code and source code, programming code, any of this sort of jargon, we're talking about lines like that. And in most programming languages, when you want the computer to do something, you express it in the form of a line of code. And sometimes the line gets a little long, but in general, one line means do something, just like one puzzle piece means do something. Well, what about loops? Last week we saw something like this: forever say, "Oh, hi." It's just going to say this and say this and say this and say this. The syntax this week and beyond is going to look a little more cryptic, but we can express the same idea. We're going to have a keyword called while. We're going to have kind of a stupid structure here where we say while true. And then in the curly braces, we're just going to say printf, which, as you can kind of infer, means print this to the screen. And what are we going to print? "Oh, hi." Now, while true, why is this equivalent functionally to forever? Well, true is always true, so it's just as though you're saying do this again and again and again, because there's no variable there. There's just what we'll call a constant, the keyword true, and it's like saying while 1, while 1, while 1, while 1. 1 is always not 0, which means it's always true. So again, 1 and true and yes are all synonyms for our purposes thus far. Well, what about loops like this? Repeat 10 times, say, "Oh, hi." Well, we need a slightly different construct because while true kind of implies an infinite loop. But there's this syntax in C called a for loop. And again, we'll come back to this. This doesn't all have to sink in now. But you say something like for int, and int's going to mean integer. Int I is going to be a variable. So set I equal to 0. Then do this loop so long as I is less than 10. And every time you do something, go ahead and increment I with plus plus. So there's going to be shorthand notation like this, plus plus, which just means increment. Add 1 to a variable. And we had a puzzle piece quite like that in Scratch. Add 1 to some variable puzzle piece. Well, variables in Scratch looked indeed like this. Set counter to 0. Forever do this. Say counter, change counter by 1. So this should just say 1, 2, 3, 4, 5, 6. Infinitely long. How can we implement that in C? Well, we need a variable, so it's going to look like this. Int counter gets 0, or equals 0, while true. And now we kind of steal some syntax from previous examples. The printf, the plus plus, but the idea is the same. So again, even had we shown you the text in white in the first week, it's kind of overwhelming, it's kind of confusing, it's not all that intuitive at all, but the ideas are exactly the same. And this is why we start with Scratch, because it gets across the ideas without the stupid distraction of what's ultimately some arbitrary syntax that humans decided on that we all just need to acclimate to. But we will, and quite quickly. So Boolean expressions. Boolean expressions were what? How do you define them? Yeah, so true or false, something that's yes or no, 1 or 0, true or false. So they looked like this in Scratch. Is x less than y? Is x less than y and y less than z? Well, we can do the same sort of expression in C. We use some parentheses, we use some angled brackets, but it looks like this. x less than y, or is x less than y ampersand ampersand. And ampersand ampersand happens to represent the notion of Boolean and, like the anding things together. It's distinct, as we'll see, from a single ampersand. So there's some oddities like that, but it's the exact same idea. So we can do a few others. With conditions, we had something like this. If x is less than y, say x is less than y. Else, if, so remember we could embed one puzzle piece in another to have multiple forks in the road, not just one or two or three. We could keep doing this. Well, we can do this in C as well. In this case, I'm essentially saying if x is less than y, then say as much. Else, if x is greater than y, say as much. Else, say they're equal, because that's the only possible alternative if it's neither less than nor greater than. So it translates to this. If x less than y, curly braces, printf. Else if x greater than y, printf. Else, printf. And the curly braces kind of, just like the if conditions and the else conditions in Scratch kind of have these embracing yellow bars, similarly do the curly braces conjure up that same idea. It's enclosing one or more statements inside of them. Well, what about arrays? We only talked briefly about these. Maybe you've deployed them in your own program. But an array is what in English? Yeah, it's like a list. It's some kind of data structure, data storage. It's a container in which you can put 0 or more things. This is in contrast with a simple variable, because with a variable, you can just put one thing. So if you wanted to store, like in the game Fruitcraft RPG, which we played briefly last week, if you wanted to collect the apple and the orange and the pear and whatnot, you could have an apple variable, an orange variable, a pear variable. But your program very quickly gets bloated with all of these darn variables, all of which are related, and yet you need to sort of independently define them. An array lets you say, I need multiple such fruits, and I want to keep them somehow together in sort of one bigger variable, but still get at individual components as we did with the Fruitcraft RPG. So how do we translate this to C? It takes a couple lines this time, but add orange to inventory might map to something like this. String inventory bracket 1. And we'll come back to this next week, but string is synonymous with word or phrase or sentence. It's some number of characters that a human might type. Inventory is just the name of this variable. And the bracket 1 probably denotes what? Yeah, the size in this case. And we'll see this is kind of a stupid array because I'm only storing one thing, but it's meant to be a simple example. This just means give me an array of strings, of words, of size 1. So again, it's stupid in that I could just use a single variable for this, but we could just change that 1 to a 2 or a 10 or a 100, and that little character on the screen could then collect 2 or 10, 100 pieces of fruit. It wouldn't necessarily be bounded by 1. And then inventory, open bracket 0 equals quote unquote orange. We'll see next week. This is just the way of saying put the string, the word orange, inside of location 0 in the inventory. Now here we see one of the first curiosities of computer scientists. Turns out computer scientists, programmers more generally, typically count starting at 0. Why? Well, if you think about our discussion last week of bits, and even just now, what's the smallest number you can represent with a bit? Well, 0. What's the smallest number you can represent with 8 bits? 0, just 0, 0, 0, 0, 0. So why not just start counting at 0? Why waste this bit arbitrarily like humans do in speech, counting at 1? So in general, it's just easier, and it's definitely conventional to start counting at 0. Thus was born problem set 0. Thus was born week 0 last week, and so forth. We've just preserved this same tradition. So Scratch, however, does not do this, realize. They made a pedagogical decision, particularly for the target audience, to actually start counting most things at 1. So realize this is not universal, but it is quite common. So here's a complete program. So this is, again, a language called C. This is a program that I might write using a simple text editor. How do I actually get to the point of writing this program? How do I get to the point of translating this program into the zeros and ones that the computer actually understands? Well, first let's tease this apart, just to get some jargon out of the way, even though some of it we'll just keep taking for granted until it more naturally fits into the conversation. So this is a simple program, and in C, just like in Scratch, there's this when green flag clicked block that kind of kickstarts the whole program. In C, as in a lot of languages, Java, C++, and others, main is sort of the equivalent of the when green flag is clicked. If you have a main function, we'll call it. Scratch called them scripts. We'll call them functions. But they're essentially the same for today's purposes. So long as your program, the text file you're typing in on your computer, Mac PC or whatever, contains the keyword main, it's probably an executable program, something you can run, something you can double click on. Now, you can't just type main. You have to adhere to some annoying conventions. And among those conventions in C are, first, you have to say that main returns something. And we'll come back to this. But for now, just take for granted that main must be prefixed with the keyword int, int. Now, as an aside, what is this all about? Well, if you've ever used your own Mac or PC or Linux box and something weird or bad has happened, you get some error message. It freezes. Odds are you've seen a little text box on the screen that says something like an error has occurred, you must reboot, or your changes were lost. And then it'll often say something like error -1 or error 253 or some random number that's of no value to any of us. It's probably of some value to the programmer who wrote that program, because programs, or specifically functions, can return numeric values which are not often useful to people like us, but they're useful to the programmers or other parts of the program. And generally, 0 means everything went perfectly. 0 it's a little counterintuitive in that 0 we typically say is false or no, but 0 is perfect. And why is it perfect? Well, so long as you choose 0 to mean success, this program worked great, it quit without any problems, you have a seemingly endless supply of error codes that your program can return if something's indeed broken. So when you see these error messages on the screen and you see some numeric value, they're almost never the number 0, it's the number 1 or 2 or -1 or -3. And that's so that Microsoft and Apple and others have, again, so many possibilities for error codes to return. Now, it's not always error codes. We'll see other uses. But for now, the reason that main returns a number, because it's some way for an individual program to tell the OS it worked great or there was a problem. So what else is there? Void, I'm going to wave my hand at for now. But know that programs can take input when you run them by typing a command or by double clicking them. Void just means this program takes no input. It's so simple. It just does something, doesn't take any input from a human. The curly braces are what keep everything together, just like the yellow structure of most Scratch blocks. Printf is what we're going to call a function. So main is a function, printf is a function. And what's nice here is that printf, a function can call another function. Now, what's a function? You can kind of infer it from the name. It's like a miniature program that just does something. It has some functionality. So printf's purpose in life turns out to print something to the screen. Main's function in life is to kickstart a program the moment it starts running. Main is what it's supposed to do first. Now, functions here, printf has this parenthesis and then another parenthesis inside of which is a quote unquote. And just to see if we can tie the conversation together, what would you call perhaps the thing inside quotes here? Yeah, so it's a string. So we've used the word string before to just generally say a word, a phrase. So indeed, printf can take as input a string, and that string is what's printed on the screen. And that's it. All this conversation just to say, here's how you implement hello, oh hi world on a computer, but it gets us to the point now of being able to write and run this. So we need the ability now to write and run a program. So how do we do this? Well, those of you who are coming at this with prior programming experience, you probably use something like Eclipse or NetBeans or Emacs, or there's a seemingly infinite number of programs with which you can write software, write programs. But again, I could do this on my Mac. I could open up a stupid little program called TextEdit. It's analogous on a PC to notepad.exe. And I could just start typing, include standard IO, int main void printf. I'm literally just transcribing what we saw before. Oh, hi. I think I did that yesterday, too. Oh, hi, world. And again, there's some syntax in here I'm waving my hand at, the \n, the semicolon. But we'll come back to that. All I need to write software is a text editor like this. You could even use Microsoft Word, so long as you don't save it as a .doc, but you save it as like a .txt file or something like that. But that's not the right program to use. Really, you want a program dedicated to programming, as we'll soon introduce. So unfortunately, this is not quite zeros and ones. Right? I could, if I really wanted to create a nightmare for myself, write oh hi world by expressing myself with zeros and ones, saving that file with a special program, and then double clicking its icon or running some command. But this is obviously not human friendly, nor is it human friendly to feed punch cards or tape into a machine. Instead, we write programs in higher level languages like C that look like this. But what do you need, especially if you have some prior background, what do you need to do with this source code in order to convert it into those zeros and ones? Yeah. So there's this other utility that's out there, and it's called a compiler. And it's not a text editor. It doesn't let you write programs, but it lets you prepare programs for running. So step one in writing a program is just write the program in your choice of language. For now, we'll use C. Later in the semester, we'll use PHP and JavaScript. But we just need to type it at our keyboard in some simple program. But step two, usually, at least with a language called C, we have to convert this into zeros and ones by passing this file as input to another program that will essentially convert this to zeros and ones. And then once I have those zeros and ones, then I have a .exe on my desktop, to borrow Windows speak. Or I have a .app on my desktop, to borrow Mac OS's speak, whereby I can now run this program. So how do we do this? Well, if you have a Mac, you can go to the Mac store these days. You can download a program called Xcode for free if you have Lion, or you can pay some money if you have an older version. And you can then install a compiler and, again, a program called Xcode. And you can do all of this. Windows, there is no Xcode. That's an Apple product. So instead, on Windows, you go and buy a Visual Studio from Microsoft, or NetBeans, or Eclipse, or some other tool, though there are freely available alternatives. But that, too, is kind of a pain in that it doesn't come with the operating system. And in a class of this size, we'd have all sorts of people using all sorts of versions of Mac OS and Windows and even Linux and other OSs. And my God, it would be a nightmare, all using different computers trying to get all of our code to work on completely different hardware. And so thus was born the CS50 appliance. And we made a mention of this last week, but the CS50 appliance is our way of saying, use your Mac, use your PC, use your Fedora machine, your Ubuntu machine, and instead install inside of a window on your computer our operating system. Now, the CS50 appliance is going to be an operating system that runs inside of a window on your own computer. That operating system happens to be called Linux, with which you're probably at least familiar with by name. It's freely available, very popular, super popular in the world of websites and running servers, primarily because it's free and high performing. We're using a specific flavor of Linux called Fedora. There's all sorts of competing alternatives, Fedora and Ubuntu and all of these big names. We chose Fedora, but it doesn't really matter which one you use. But once you install this thing, we will all have, no matter what OS you brought to campus or what computer you brought to campus, a similar environment that looks a little something like this. And it actually looks like Mac OS or Windows. All of these manufacturers kind of put the menus in different places, and the icons might be called something trash or recycle bin. But at the end of the day, they're all stealing ideas from each other. And at the end, it all kind of looks the same. So if you look at top left here, you have a home directory. This is going to be like My Computer or Macintosh HD. You have File System, which is everything. You have the trash can. At the bottom left corner, you'll see that we don't have a Start menu. We have a CS50 menu. And inside of that is going to be links to programs. And so long story short, even if you're using Mac OS or Windows, starting this week and beyond, we're all going to be running the same OS inside of a window on our own computer. So how do you do this? Well, we'll provide you with instructions with the first problem set. But know for now that you'll download a free program, happens to be called VirtualBox. This is a program that exists for Windows, for Mac OS, for Linux, for Solaris. If unfamiliar with some of those, they're just other operating systems. And when you run it on your computer, it looks a little something like this. On the left-hand side, you see a list of all of the virtual machines that you have installed on your computer. And you see on the right the virtual specifications of those virtual machines. So what is a virtual machine? It is just a computer running inside of a window, being tricked into thinking that it's actually running on a physical hardware CPU with physical RAM and a physical hard drive. But no, I mean, we've gotten so sophisticated as a society that we can actually trick Windows and trick Linux and even, with some effort, trick Mac OS to thinking that those operating systems are not running on, that those operating systems are running on a piece of hardware, a computer that you bought at the store or online. But in reality, you're actually running it inside of a window on a computer that you bought online or in some store. And you can really mess with your mind if you think about running a virtual machine in a virtual machine in a virtual machine, but that tends not to work so well. So you kind of do it once and you leave it at that. But what's the advantage here? Well, just as an aside, and this is really just a teaser for things to come, these days, most of your laptops, if relatively new, have probably one CPU but multiple cores. You might have 2 cores typically. Well, these days for servers, you might have 16 cores, 32 cores. And that's essentially equivalent to having 2 or 32 or more brains inside of your computer, all of which can do something literally simultaneously. Now, the world is not very good at taking advantage of 32 CPUs, even 2 CPUs. We humans, we don't check our email all that quickly, despite what you might think. You don't need 2 gigahertz of power times 2 to check your mail. So even our computers have a lot of spare resources, at least if they're 3, 4 or years old or newer. And so what virtual machines take advantage of is all of the spare brain power and memory and disk space that we just don't typically use. You don't use all of your computer's resources for Microsoft Word, for instant messaging, for Facebook, and the like. So the virtual machine is going to borrow some of your CPU cycles, so to speak, some of your RAM, some of your disk space. So what you see here in the CS50 appliance, you will download essentially a zip file, a compressed file from the course's website for the next P set. When you follow the instructions, you'll see that the virtual machine you're installing has, turns out, 768 megabytes of RAM. Now, by modern standards, that's actually not all that much. And we could crank it down even further, because most of your laptops have at least a gig or 2 or 4 or 8 these days. So realize these are all configurable. But once you then double-click CS50 appliance at top left, voila, your Mac becomes Linux, or your PC becomes Linux. And if you maximize the screen, you don't even realize what operating system you're actually running. And so now we are all on the same page. Now, as an aside, I've also had this icon here. I just for fun installed Windows in advance on my Mac inside of a window, so that also in class moving forward, if we ever want to have a conversation about what something looks like on a Mac or a PC, I don't need to have 2 separate computers. I can use just the Mac by default, but then open a Windows window, and we can see what it would look like for the half of you or so that run Windows 7 or XP or Vista. So realize that's another advantage as well, to run multiple operating systems at once. So enough about what the technology is. Let's actually use it and do something interesting. So once I double-click this icon, a few seconds or minutes later, the operating system would boot up in a window. If I maximize it here, I now have my home directory, like my computer, and I have the trash, I have this menu at bottom left, and I have all sorts of programs which we'll explore over time. But the one that I care about first happens to be under programming. And you'll see there's a few things under programming. One is called gedit. There's a few other things. We actually installed Scratch in the appliance, even though you didn't need the appliance for the first P set. We just put it there so that, in theory, you could take the whole course inside of this appliance. We'll see a program called Eclipse later in the semester, which is an even fancier tool with which to write programs. And we'll see Terminal as well. But for now, I just want gedit. Gedit is going to be a slightly better version of TextEdit on a Mac and Notepad on a PC. And it's still pretty simple. I mean, it's mostly a white screen with very few menus. But it's in this area here in the middle that I'm actually going to start writing my programs. And it's at the bottom of my screen here where it says jharvard@appliance. And there's this blinking prompt. That's where I'm going to run my programs. So typically in a Linux environment, you don't have to double-click icons. You can actually type the name of the program at a prompt, hit Enter, and that program will run. And that's where we'll start to keep things simple. So let's give this a try. I'm going to go ahead and first increase the font size here, just so we can zoom in. But this is just for the sake of lecture here. So now we've got a bigger font. And I'm going to go ahead and save this file like I would on any operating system. Save as. I'm going to go to my desktop just for kicks. And again, all this looks a little different for Mac OS or Windows, but it's the same thing once you get used to it. Hello.c. So the convention when writing programs in C is to call them something.c. So now I'm going to save this on my desktop. The file itself contains nothing. Let's just do a sanity check. If I minimize this window for a moment, there it is. It's just a file just like Mac OS or Windows. There's nothing in it because it's just this big blank text file. So let's start coding. Let's start programming. Include standard.io.h. We'll come back to that in a moment. Int main void. I remember seeing that before. Here's some curly braces. And then the command was printf oh hi world exclamation point /n semicolon. Now, I've done this sometime, so it kind of gets easier over time. But that is a transcription of what we had before. So it's very underwhelming, even though it might syntactically be a bit ugly. But let's actually run this thing. So first, I'm going to hit save, either with Control-S, or I can do it sort of old school, file, save. And now I've saved the file on my desktop. But now I need to run it. But not yet. What needs to happen before you can run it? we need to compile it. So it turns out that in a Linux environment, and also in a Mac environment, and also in a Windows environment, if you download the appropriate software, but the instructions vary by operating system. So again, we're standardizing here. Notice that at the bottom of this screen, inside of gedit, I have this, again, blinking prompt. So what the appliance does when you boot it up is, even though we could give you all unique usernames, it's just kind of a pain to create a username and password for a program that's running on your own computer. So instead, we decided that everyone will take on the identity by default of John Harvard. And John Harvard's username is jharvard. And so when John Harvard is automatically logged in, you have his blinking prompt and his home directory, his folder of storage. But when you submit, well, that's at the point we'll ask you your actual name and so forth. But for now, only you can access this account. And notice at this prompt, I can do certain things. In Linux, and this is what we're seeing now, the operating system Linux is very often navigated by way of textual commands, not by clicking and pointing. And so the textual command we'll say first is ls. ls is shorthand notation for list. And when you hit ls and hit enter, what you see is a list of all of the files and folders in John Harvard's default directory or folder. John Harvard's default directory or folder is conventionally called his home folder. So in Windows, this would be My Documents. In Mac OS, this would be Documents. In Linux, it's Home Directory. So we're in my home directory, and you can see that you have a desktop folder. And also, because I was doing a bit of prep work, I also created a lectures folder. And they're in bold just to kind of convey to me, the human, that these are directories. So I want to actually go where to compile this program? So it's on my desktop. Indeed, it's not in this directory. So instead of double clicking, which we could do, again, we're starting at the simplest form here, I can do cd desktop and then hit enter. And notice what happens. My prompt just changed. So in the interest of user friendliness, we've pre-configured the appliance to always remind you where you are by just telling you parenthetically what directory you're in. Otherwise, it's very quickly to kind of get lost or forget where you CD'd into. So now I'm in desktop. So if I type ls, I'll see the file I created. I don't see trash. I don't see file system. I don't see those fake icons that are just there to be user friendly. I only see actual files and folders that I put there. So there's hello.c. So now I need to compile this. So how do you go about compiling a program? Well, there's actually a few ways, but they all produce the same result. The simplest way to translate a program written in C to zeros and ones is with a command called gcc, GNU Compiler Collection. It's a very popular, very standard, very robust program that simply makes you type gcc space the name of the program you want to compile, and that's it. It does all the conversion for you. So if I go back to gedit here, and then let me zoom in just so it's nice and big, and I type gcc hello.c enter, the fact that nothing happened is actually wonderful. In fact, when you sit down to write your first program and something does happen, that means you made a mistake. Because what you'll see is a whole bunch of error messages. You left off a semicolon, or you did something wrong. Whereas Scratch isn't quite as pedantic and doesn't yell at you. It just doesn't work. GCC will check your code and say, I'm not converting that to zeros and ones. There's some mistake or mistakes. But no error messages is good. If I now type ls, you'll see two things. I have just created a program that by convention is called a.out. This is something like whatever.exe in in Windows, or whatever.app in Mac OS. So a.out is just the default name for a program. So to run it, double clicking on this is not going to have any effect. This is just text. I can run /a.out. So a.out, and then just as an aside, the / is for the following reason. Because this is a stupid little program I myself wrote, and it didn't come with the operating system, I didn't run an installer, because it's in my current directory, I can't just type its name like I typically can on a computer and it just knows where to look. I have to tell it where to look. And so in Linux and Mac OS and even in Windows, if you use the right tools, dot is shorthand notation for the current directory, wherever I'm in, whatever folder I opened. And as an aside, anyone know what the parent directory is if you want to go backwards? It's going to be .. So we're going to see conventions like this. But for now, dot just means look here, and slash just means here / file name. So enter. Oh my God, I wrote my first program. Like a.out contains now zeros and ones, and they're in a nice specific pattern that's understood not only by the operating system, but also by the CPU. Intel inside is relevant here because the zeros and ones that GCC outputted are structured in such a way that these zeros and ones mean print, these zeros and ones mean quit, these zeros and ones mean add, these zeros and ones mean subtract, and so forth. There are conventions that Intel and others have decided on. So unfortunately, this is kind of a stupid name for a program. So I can actually improve upon this so that when I write my programs, I don't have to brag to my friends. I just wrote a.out, which would be nice to give it a name like hello. So to compile a program with a specific name, we just introduced one new idea. Most programs that you run by typing their names at a prompt take what are called command line arguments, or options, or switches. Any of this jargon is relevant. And here we're saying GCC -O. The O happens to represent outputs, and I know that just from reading the documentation. So GCC -O, hello, then hello.c, with spaces in between, are saying compile hello.c and output it to a file not called a.out, the default, output it to a file called hello. So now if I go back to my prompt and zoom in, I can recompile this with GCC-O, hello, then the name of the source code, hello.c, enter. Nothing seems to have happened. ls, though, there's hello, but that doesn't work. Why? Right. So // is important only because, again, this is not a standard program that I bought and installed or downloaded. Rather, I wrote it. It's in my own little directory, which means I need to be more explicit. And /hello indeed runs that program there. So you know what? We can actually simplify even further, because you'll soon see that GCC-O hello 1 just gets hard to remember. 2, it just gets tedious. My God, just to compile your program, you have to type all these commands. But as an aside, realize that Linux comes with all these tricks. Right now, I'm hitting the up and the down arrow on my keyboard, and it's remembering seemingly an infinite supply of things I've typed before. So there's lots of little tricks like this. If you want to do what you just did, you can typically hit up and hit enter, and it will just do it again. But I can do better than that. To compile a program, I can also just make it. There is another program on Linux called make. And make figures out for you typically what types of GCC commands need to be executed in order to compile your programs. Because we're doing something fairly simple right now. But if I actually do make hello, this will actually make a program called hello and figure out what to type for me. So let's do this. I'm going to go ahead and type just make hello. Notice the dichotomy here. I'm not typing make hello.c. I'm typing just make hello. And the program's going to assume if I've said hello, it will look for a file called hello.c. I hit enter. OK, well, that's even more friendly. It's saying, I don't even need to compile this into zeros and ones because you just did this. Well, I really wanted to do it, so let me remove those files I created. The command in Linux to remove files is rm, remove. So there's a pattern here, right? Rather than ever type really a whole word, the folks who invented Linux and Unix and these other operating systems tried to make the commands as compact as possible. So rm means remove. So I can remove hello. I'm going to also remove a.out for good measure. So just putting a space and separating them on the same line will then prompt me remove regular file hello, whatever that means. So y for yes, enter. Remove regular file a.out, y for yes, enter. Now if I do ls, notice we're just back to where I started with just hello.c. So let me go ahead now and run make hello, enter. And notice even more stuff appeared on the screen. And this is because we've pre-configured the compliance to know about all sorts of useful commands that, my God, it would be a pain in the neck to type that whole line of code every time you want to compile a program. So make is going to automate this for you. And we'll tease apart over time what these various flags or switches mean. But for now, the compelling feature is that we have a program called hello. I can go ahead and run it as such. And now I have oh hi world executed much more succinctly. Yeah?
Really quickly, so programs that are actually runnable are in bold?
Programs that are actually runnable are typically in this program written in bold as are directories. And it's just a convention. It will differ in different programs. So just to tease you with one other thing. So this is, again, the CS50 appliance. If I minimize this, we're back at our desktop. But realize this is a full-fledged modern computer. I can click the Firefox icon, and I can go to google.com inside of the appliance and actually now do everything I could on the internet inside of this machine. Moreover, what's nice about the appliance, irrespective of the internet, is that especially in the dorms and houses, if you have kind of flaky wireless, you don't need to be constantly connected to the internet. The appliance boots independent of the internet, so you can now work anywhere, anytime, including over breaks, if that's at all appealing, without actually needing to be perpetually online. And it's all irrespective of what your actual operating system is. Any questions? All right, so that's a lot to absorb all at once. Why don't we? Oh, yes. Good question. Why is it make hello and not make hello.c? Honestly, just because. Like the program's authors decided that if you type make hello, it will assume that you want hello.c, and it will look for those files. We'll also see that it's more motivating in future weeks because you can create nicknames so that when you say make something, something can be defined by you as doing a sequence of steps that you wanted to automate.
What would happen if you had another file like that that was hello?
If you had another program called hello, but you wanted to compile hello.c, would it get confused? No, because that's what we did a moment ago. I still had the hello program, but so I typed make hello, and it said, it's up to date because it had already been compiled, and it realized that it would create the same output. So in short, no. Yeah?
If you were to type make hello.c, would it have done the same thing?
Good question. So, and actually, I can emphasize this quite explicitly. When in doubt, honestly, when you have a computer, when you have a keyboard in front of you, try it. The worst you can do is screw everything up and download a new appliance. So make hello.c, enter. Nothing to be done for hello.c. Well, the last time I saw that, it related to this. So let me get rid of this. So now let me do make hello.c. It doesn't want to compile it because what it's now looking for, it's now realizing that this is not a file that needs to be compiled. So in short, error message, though it's not explicitly clear that this is a problem. Yeah?
Do the files you're creating exist in a real directory on your hard drive, or is it all?
Really good question. Do the files we create, like hello.c, exist in a file on your own hard drive? Actually, no. If you poke around your own Mac or Windows hard drive, you will just see one huge file. It's called a VMDK file, virtual something or other. And that means that all of the files you create inside of the appliance are actually hidden inside of 1 gigabyte file. And that gigabyte is chopped up into the individual files. But you'll see over time in the specifications for PSETs and in the online documentation, you can interact with the appliance, with your own computer. That home directory that John Harvard's files are stored in, you can actually mount that on your own computer. You can connect to it via various internet programs. So in short, you will see that we can interact with this in all sorts of ways, especially if you find this environment just unappealing or confining. You won't strictly need to use it. There's many ways to make use of the appliance still. So this is a lot to absorb all at once. Let's take a 2-minute break to kind of give you a moment's respite, and we'll resume with something more fancy. All right. So we are back. If at any point, honestly, you're confused, have questions, please catch my eye, raise your hand, or I'll certainly stick around afterward. Moreover, moving forward, in addition to PDFs of slides and source code being available online, realize that all of the programs we write in class will either be posted in advance on the website, or if we create it on the fly, we'll post it right after lecture so that you can download it to your own Mac or PC inside of the appliance. And so even if you want during class, if you find it helpful to play along and actually type what I'm typing, get the same error messages I'm getting, realize you can run the appliance in Sanders here on your own machine. The wireless is pretty spotty in Sanders right now. They're working on bolstering that for later in the semester. But if you do download the appliance back home or somewhere else on campus, then next time bring it to class, realize it's a good way to more actively engage rather than just sitting there listening passively. So a couple of more building blocks with which we can do more interesting things. So again, a function is a chunk of code, a chunk of lines of programming code that do something. And what do? It's really up to you. Main is entirely up to you because what you put in main, just like in Scratch, what you put in when green flag clicked, is what happens when you start running the program. Now printf you can control its behavior only to some extent. Printf is another function whose purpose in life, again, is to print something to the screen. But the F actually denotes something. It means formatted. Because even though we've been using it for very simple things, oh, hi, world, you can actually print numbers and characters and whole words and sentences and other things. You can format numbers as integers, as real numbers with decimal points and all sorts of other conventions. And so printf takes what are called arguments. So when we saw printf before, recall that we saw these parentheses inside of my program. And anytime you see parentheses after the name of a function, that's your way of modifying its behavior. If you think back in Scratch with all those puzzle pieces, sometimes you could type a number into a little white box, or you could drag a puzzle piece on top of another, and it would sort of magically grow and then contain it. Well, same idea here. You can modify the behavior of puzzle pieces and functions by passing them arguments. It's just in C, you have to be a little more deliberate with the keyboard. And so anytime you see parentheses right after a function name, that means it's taking input, generally called arguments or parameters. But these are, for our purposes, now synonymous. It takes input. Why is that useful? Well, it'd be a pretty stupid function if all printf could do is print oh, hi, world. It'd be nice if it could print anything. And indeed it can. I just have to choose as the programmer what to pass in between double quotes. Now, any guesses as to what this \n at the end has been representing? So new line. So computers, again, are pretty dumb. They only do what you tell them to do. And if you don't tell them to move the blinking cursor to the next line, it's not going to do it. So if I actually omit this, save my file, and let me zoom in, and then rerun make hello, enter, and then run hello, notice what happens at the prompt. It's kind of a mess. It says, oh, hi, world, exclamation point, but then the prompt reappears. And that's because I've omitted the \n. And we'll see there's other ones. There's \r and \t, but \n is by far the most commonly used in C and in other languages. So what else do we want to know about? Well, in C, you have the notion of variables, which we'll see in a moment. But these variables are of specific types. There's a char, which represents a single character, the act of touching one key on the keyboard. There's an int, which is an integer. Now, an integer, as an aside, is 32 bits. And we only had 8 bits on stage before. With 8 bits, you can represent how many different values? It's actually 256. How do you get there? Well, if you have 8 bits here, and each of these bits or volunteers can be a 0 or 1, there's 2 opportunities here, 2 opportunities here, 2 opportunities here, 0 or 1, 0 or 1. So if you multiply all those together, 2 times 2 times 2 times 2, that's the same thing as 2 to the 8, and that's 256. So now if you have a 32-bit number, not an 8-bit number, but a 32-bit number, that's 2 to the 32, which is roughly, anyone know? It's actually 4 billion, give or take. So 2 to the 32 is 4 billion. Now, what's the takeaway? That means an integer in a computer can store the number from 0 to 4 billion, or more typically, from negative 2 billion to positive 2 billion, give or take. But notice the key takeaway here, it's finite. There's only a fixed number of bits, which means there's only a fixed range of values, which means at some point, if you try counting up to 2 billion, 2 billion 1, 2 billion 2, 2 billion 3, eventually what's going to happen? You're actually going to end up being back at 0 or a negative number. Some crazy thing's going to happen where your counting is actually going to wrap around, and bad things then happen as a result. So how do you get even bigger numbers? Well, you use bigger integers. You use 64-bit integers. So if you've heard that your PC or Mac these days is 64-bit, that means that all of the numbers with which it performs math are now 64 bits. And that generally is good for speed and performance, but it also means older programs that are 10 years old or more often will break on that computer. So we are using, as an aside, a 32-bit virtual machine so that it works on anyone's laptop, even if it's several years old. But there's other data types. Chars are 8 bits. Ints are 32 bits. Float is also 32 bits, but it's what's called a floating point value, a real number, where the decimal point can actually it's a real number with a decimal point. Now, there, too, if you think about it, real numbers, we were taught in grade school, can be infinitely precise. You can have 0.3333333, and you put a little line over it, which means infinitely many threes. That's really darn precise. It means 1/3 exactly. Computers, you're going to have to stop writing down threes at some point, right? Just conceptually. Even if bits are completely new to you, it stands to reason that if you only have a fixed number of them, whether it's 8 or 32 or 64, at some point you're going to have to decide, do I want to represent 0.3333333, or 0.444444. In other words, there's only a finite number of permutations of zeros and ones, only a finite number of permutations of these 8 humans on stage. So you've got to pick which of those real numbers do you want to represent. So in short, computers are inherently imprecise, and this can actually create some significant problems. If you think back some 10 plus years, the Y2K problem, which is one of the more recent times when everyone thought the world was going to end, well, what was the Y2K problem? What was the source of that issue and all the drama? Yeah. Yeah, exactly. So in a lot of computer programs, the date accidentally went from 1999 back to 1900 because the programmers made the judgment call, good or bad at the time, to, no one's going to be using my software in the year 2000. I'm just going to use 2 digits to represent the 2 numbers after the 19. So the problem, though, is if you're only using 2 digits and you get to 1998, so 98, 99. What do you get when you want to hit 2000? You need the number 100, but if you're only using 3 decimal digits, you're kind of out of luck. So what did these programs do in Y2K? They wrapped around back to 00, so all of a sudden people's dates were 1900, and just bad things happened. The world did not, in fact, end, and in fact, a lot of people made a lot of money fixing all these problems, but using fairly arcane languages at that time. But the point was that that was just a design decision, arguably a foolish design decision, but if you can imagine from the 10,000-pound computer, memory was expensive back in the day, and it wasn't all that large. So you wanted to cut as many corners as possible, but it turns out that people were still using software that's 20 years old, 30 years old. And I don't doubt on campus there's computers that are still running software that old, and they've just been patched together over time. So what can you do when you need a bigger number than 32 bits for an int or a float? Well, there's ironically, you'd think it would be a long number, but it's in fact not. It's usually a long. So we'll see that you call the data type, the type of number, it's a long, and that typically gives you 64 bits. If you want even more precision for that decimal point, you can instead use a double, which is a 64-bit real number. It's still finite. So you cannot, in fact, represent all possible values, despite what we learned in grade school. You have to choose a finite range of them. So again, that means that computers are inherently imprecise. So how do we actually use these things? Well, we've only seen printf as a function thus far, and so we've actually seen way more functions or puzzle pieces in Scratch. So let's round out a few more. So in C, it's actually not all that easy to get user inputs. You kind of have to jump through some hoops just to see what the user typed, and not to mention convert what they've typed from ASCII characters to actually numbers. For instance, when you type in 1.5 on a keyboard, that's not a number. That's actually the character 1, the character period, the character 5. So you have to kind of convert that to a floating point value. And how we do that we'll ignore for now, but suffice it to say some work has to go in to getting user input. So we have what's called the CS50 library, which is a suite of functions that you can use in your programs, and indeed we do for the first several weeks, and the names imply what they do. If you want to get a character from the user, we're going to call get char, or get double, or get float, or get int, or get long, or get string, depending on the data type, and that's going to allow me to write programs like this. Let me go back to my code here. Let me go ahead and say not just oh hi world now, but let me declare a variable, and in C you declare a variable like this, string s, and I'm going to go ahead and say get a string from a user. And getString, just like printf, is a function. But what's neat about getString is that it doesn't just do something and leave it at that. It does something, and then it hands it back to me. All right, so it's as though this is doing my bidding. getString, it's going to deal with all the complexity of keyboard input. It's going to get that string of characters from the user, and it's going to hand it to me in such a way that I can store it inside a variable, just like Scratch. And I'm going to call it s, and the type of that variable is what we'll call a string. If you're familiar with Java, it's not capital S, it's lowercase s string, but it's just a variable. And that's because of the CS50 library. Now, again, I said that we don't always have to type oh hi world. We can pass in an argument whose value changes. So it turns out in C there is these placeholders. And if I do not just a hard-coded string of characters, I do %s. That means put a string here. Well, what string do you want to put there? Well, let me go ahead and just move outside of the quotes, comma, s, And what we'll see here is that some functions can actually take not just 0, not just 1, but even 2 arguments. And the convention in programming is to separate those arguments, those inputs, those parameters, again, all synonyms, by a comma-separated list of arguments. So now what's going to happen? Well, whatever I typed is going to get printed, and that is going to be because the s gets substituted for the %s here. But I need to do one more thing, and I can finally now explain what was going on here. This include standard.io.h is what's called a header file. It turns out that I can't just start using things like printf and just assume that they'll work. I have to tell the compiler, I want to use a function called printf written by someone some 20, 30 years ago, and that function is declared. It's written in a file called standard.io.h. Now, I don't know where that is. It's somewhere on the hard drive. But the compiler knows where to look by default. So that's why I was able to use printf. If I had omitted the highlighted first line, I would have gotten some kind of error. Same thing with the CS50 library. If I want to use the CS50 library, I have to say use CS50.h. And I don't know where this file is. It's somewhere in the appliance's hard drive. GCC will find it for me. But now I have the ability to use the getString function as well. So you didn't have to do this in Scratch. Scratch makes everything available to you at once. But now I have to be a little more deliberate. And that's OK. It keeps my programs even more explicit as to what's going on. So let me zoom in again. Let me type, what do I type to compile this? Yeah, it's kind of there, right? You can always cheat there. So make hello, enter. OK, no errors, so that's good. Run hello. Nothing seems to be happening, but I do have a blinking prompt, so I can say something like David, enter, and kind of a bug. I don't really like that output. What can I do to fix? Yeah, \n there. And I can make this a little more user-friendly. I can say something like printf name please :space. And again, a semicolon. Turns out this is just a convention. At the end of most any statement in C, you have to put a semicolon. So now I have a 3-line program. Let me go back here and rerun it. David, didn't fix. OK, good. Right, so just because I changed the source code doesn't mean the program itself is going to start working. So let me actually rerun make hello. That looks good. Now let me rerun hello, enter, name please. That looks prettier. Enter, David. Now you can imagine making even more sentence structure there. But now we have the ability to get input and get output. But let's take a look at just one other format string. Turns out I'm going to go ahead and get a float from the user. And I'm going to have to change this now to float f. And the name of my variable, I'm just keeping it simple. F for float. I only have one variable. There's no confusing it with something else. I'm going to put %f here and f here, because now I want to say, just give me a number, please. So let's go ahead and run this program. So let's go ahead and run make hello. Run hello. Number, please. Let's do 1.5. Enter. Interesting. That looks pretty precise. That's a lot of zeros. But it turns out we can reveal to ourselves, at least for educational purposes here, I actually want to see what number's really being stored there. Let me go ahead and show 10 digits after the decimal point. So I'm changing the format string. Instead of just %f, I'm doing %.1f. But that's just so I'll see more on the screen. So let me rerun this. Make hello. Let me rerun hello. Enter 1.5. Interesting. So that's actually a pretty good number. Let's try something else. Let's run it with 0.1. Enter. That is not what I typed. So why did this just happen? I'm pretty sure I did not type 0.1000015. Why does the computer think that's what I indeed stored in the variable? Yeah?
It doesn't have enough precision to represent 0.1 exactly.
Exactly. It doesn't have enough precision to represent that number, 0.1, simple as that number is exactly, because if you only have 32 bits, you've got to pick and choose which numbers you will be allowed to represent, so it rounded to the closest possible match. Now, this might seem like a silly bug or issue, but it can actually lead to very serious problems. And indeed, to help visualize this, there's some very famous examples in history of programs and real-world things that have been implemented in software, and that software is flawed because humans like us literally have made mistakes as simple or as trivial or as innocent as that. And you'll see from this video some of the things, both with real consequences or not, that tend to happen. So let me go ahead and pull this up. It's just a few minutes long, and we'll see what indeed can happen and just how severe and how important an understanding of these low-level primitives are when you're actually making decisions to buy, to write, or to actually use software like this.
We now return to engineering disasters on modern marvels. Computers. We've all come to accept the often frustrating problems that go with them. Bugs, viruses, and software glitches are small prices to pay for the convenience. But in high-tech and high-speed military and space program applications, the smallest problem can be magnified into disaster. On June 4th, 1996, scientists prepared to launch an unmanned Ariane 5 rocket. It was carrying scientific satellites designed to establish precisely how the Earth's magnetic field interacts with solar winds. The rocket was built for the European Space Agency and lifted off from its facility on the coast of French Guiana.
At about 37 seconds into the flight, they first noticed something was going wrong, that the nozzles were swiveling in a way they really shouldn't. Around 40 seconds into the flight, clearly the vehicle was in trouble, and that's when they made the decision to destroy it. The range safety officer, with tremendous guts, pressed the button, blew up the rocket before it could become a hazard to public safety.
This was the maiden voyage of the Ariane 5, and its destruction took place because of a flaw embedded in the rocket's software.
The problem on the Ariane was that there was a number that required 64 bits to express, and they wanted to convert it to a 16-bit number. They assumed that the number was never going to be very big, that most of those digits in the 64-bit number were zeros. They were wrong.
The inability of one software program to accept the kind of number generated by another was at the root of the failure. Software development had become a very costly part of new technology. The Ariane 4 rocket had been very successful, so much of the software created for it was also used in the Ariane 5.
The basic problem was that the Ariane 5 was faster, accelerated faster, and the software hadn't accounted for that.
The destruction of the rocket was a huge financial disaster, all due to a minute software error. But this wasn't the first time data conversion problems had plagued modern rocket technology.
In 1991, with the start of the first Gulf War, the Patriot missile experienced a similar kind of number conversion problem. And as a result, 28 people, 28 American soldiers were killed and about 100 others wounded when the Patriot, which was supposed to protect against incoming Scuds, failed to fire a missile.
When Iraq invaded Kuwait and America launched Desert Storm in early 1991, Patriot missile batteries were deployed to protect Saudi Arabia and Israel from Iraqi Scud missile attacks. The Patriot is a U.S. medium-range surface-to-air system manufactured by the Raytheon Company.
The size of the Patriot interceptor itself it's about roughly 20 feet long, and it weighs about 2,000 pounds. And it carries a warhead of about, I think it's roughly 150 pounds. And the warhead itself is a high explosive, which has fragments around it. The casing of the warhead is designed to act like buckshot.
The missiles are carried 4 per container and are transported by a semi-trailer.
The Patriot anti-missile system goes back at least 20 years now. It was originally designed as an air defense missile to shoot down enemy airplanes. In the first Gulf War, when that war came along, the Army wanted to use it to shoot down Scuds, not airplanes. The Iraqi Air Force was not so much of a problem, but the Army was worried about Scuds. And so they tried to upgrade the Patriot.
Intercepting an enemy missile traveling at Mach 5 was going to be challenging enough. But when the Patriot was rushed into service, the Army was not aware of an Iraqi modification that made their Scuds nearly impossible to hit.
What happened is the Scuds that were coming in were unstable. They were wobbly. The reason for this was the Iraqis, in order to get 600 kilometers out of a 300-kilometer range missile, took weight out of the front warhead. They made the warhead lighter. So now the Patriot's trying to come at the Scud, And most of the time, the overwhelming majority of the time, it would just fly by the Scud.
Once the Patriot system operators realized the Patriot missed its target, they detonated the Patriot's warhead to avoid possible casualties if it was allowed to fall to the ground.
That was what most people saw as big fireballs in the sky and misunderstood as intercepts of Scud warheads.
Although in the night skies, Patriots appeared to be successfully destroying Scuds, at Daharan, there could be no mistake about its performance. There, the Patriots' radar system lost track of an incoming Scud and never launched due to a software flaw. It was the Israelis who first discovered that the longer the system was on, the greater the time discrepancy became, due to a clock embedded in the system's computer.
About 2 weeks before the tragedy in Bahrain, the Israelis reported to the Defense Department that the system was losing time. After about 8 hours of running, they noticed that the system was becoming noticeably less accurate. The Defense Department responded by telling all of the Patriot batteries to not leave the systems on for a long time. They never said what a long time was. 8 hours, 10 hours, 1,000 hours. Nobody knew.
The Patriot battery stationed at the barracks at Daharan and its flawed internal clock had been on over 100 hours on the night of February 25th.
It tracked time to an accuracy of about 1/10 of a second. Now, 1/10 of a second is an interesting number because it can't be expressed in binary exactly, which means it can't be expressed exactly in any modern digital computer. It's hard to believe, but use this as an example. Let's take the number 1/3. 1/3 cannot be expressed in decimal exactly. 1/3 is 0.333 going on for infinity. There's no way to do that with absolute accuracy in decimal. That's exactly the same kind of problem that happened in the Patriot. The longer the system ran, the worse the time error became.
After 100 hours of operation, the error in time was only about 1/3 of a second. But in terms of targeting a missile traveling at Mach 5, it resulted in a tracking error of over 600 meters. It would be a fatal error for the soldiers at Daharan.
What happened is a Scud launch was detected by early warning satellites, and they knew that the Scud was coming in their general direction. They didn't know where it was coming.
It was now up to the radar component of the Patriot system, defending Daharan, to locate and keep track of the incoming enemy missile.
The radar was very smart. It would actually track the position of the Scud and then predict where it probably would be the next time the radar sent a pulse out. That was called the range gate.
Then, once the Patriot decides enough time has passed to go back and check the next location for this detected object, it goes back. So when it went back to the wrong place, it then sees no object, and it decides that there was no object, it was a false detection, and drops the track.
The incoming Scud disappeared from the radar screen, and seconds later, it slammed into the barracks. The Scud killed 28 and was the last one fired during the First Gulf War. Tragically, the updated software arrived at Daharan the following day. The software flaw had been fixed, closing one chapter in the troubled history of the Patriot missile. Patriot is actually an acronym for Phased Array Tracking Intercept.
So suffice it to say, there's all sorts of non-militaristic applications of this stuff, but it's frightening just what the implications are. And so over the next few weeks, what we will do is focus not only on doing, but on understanding exactly how all of this stuff works, so that you yourselves are empowered to build most anything you would like by term's end. We will see you on Friday.